Hello and welcome back to compiler programming. In the last video, we did this refactoring to extract the encoding of the P data section, or R data section, sorry, into a separate function, which allows to estimate the size of that code before it is actually used in any other calculation and before we are writing it out, which is pretty neat. This also means that right now we don't have any hard-coded stuff in the header of that section, except for the name, but that's a static thing that we do know, and characteristic is also a static thing that we do know. So this is good. And basically probably the last fixed mute that we have in the main code here is to take care of the size of the machine code, but this stuff we also already know pretty well. So let's do that. Just that we can just put the max code size right here right away, but even better would be to do the same trick as we did with the R data and actually encode it into a separate buffer, and only then put something into these values. So this is kind of our data stuff, and we can do the same thing for the rest of the code. Okay, so we do need to know the offset of this virtual address of the text segment, but because it is basically the last segment, we can do it over here, and that would be just fine. Okay, so let's check on our code. This is what we have for our data. We are writing it out. Actually, this assert is no longer necessary because we might have more data if we input in more function. It will just go out for no good reason. And that means that we can also remove this stuff. And the whole writing out is now pretty straightforward. We are just going to the right location. We are getting the memory, so we are allocating the bytes that we need to write. We are writing out those bytes, and then we are moving to the next section. So this is kind of nice. Technically, we don't need this because there is another move over here, but for now, I'm just gonna keep it. And now what I'm going to do is I'm gonna take this stuff over here and move it to a separate function, the same way as we did for our data. And here I will basically do the same stuff as we did here, which is just allocate the right size and copy it out to the output. Again, we can change this code over here for writing out the file to actually do it in separate steps, because all the data is prepared and right now we're just copying it between buffers for no good reason, but that can be done as an optimization step, and right now I'm more concerned about the functionality and making it right. So, okay, let's take this stuff. This is gonna be text or code memory is allocating this. We will have code buffer, and this is code memory. This is going to be code buffer and code buffer. Okay, that looks good to me. Now we can create that. Again, we will start with a buffer. If we realize we need more things, we can add them, but I don't think we do. I think that Actually, we will need more things because there is this address of entry point, which is patched after the fact, and base of code. Well, base of code actually we do know, but address of entry point is definitely something that we only know later. It's also interesting that the size of initialized data is now, I guess, no, it's written out here, which means we can move it to the right place. But again, that is fine. We just need the address of entry point returned. So we're going to do the same thing as we did for this our data section. So we'll have type def struct encoded machine code, or we can say text section, and here will be some function encode text section. Okay, obviously it will get the program pointer because that's what it needs to know, and later we will figure out what else does it need. For now we will fill in this stuff, so that's going to be buffer, and we also need this address of entry point. So this is RVA, which means it is a 32-bit integer, and we say entry point RVA. That is pretty straightforward. We also want to return this thing from our program, so let's do that. Result is this stuff. Actually, we probably want to make buffer right away. And this is a place where we do this estimation, right? So I guess we... Yeah, I think we can do it there. The only thing is we also need to update this side of our data here, but I guess we are going to be doing it differently. Honestly, I'm not a very big fan of this loop because we actually want to do it step by step ourselves. So, okay, we know the size of the headers. So once we know the size of the headers, we know the size of virtual address here and so on and so forth. But this is not a very automated process, and I'm not sure I like how this is done. So we'll see if we want to change these things around. For now, though, I will bring this stuff up here and see what we can do with it. Okay, so we have my code size, we align it to file alignment, and we make some assertion, and we are good to go. So this stuff is also maybe something we can report separately to not cast there, or we can cast it there. I guess this stuff we can do somewhere over here. Maybe. I'm not sure. We'll see where this actually goes. For now, I'll just add something for myself to notice that I need to do something. Let's add fix me here. Okay, we have max code size. So we can say that the buffer is buffer make, right? That's the name of the method. Let's make buffer. Okay. Let's just copy this thing from here. And we'll get back to that fix me, hopefully, at the end of this video as well. And max code size. All right. So now we don't have a hard-coded buffer size. We can estimate exactly how much we need, and we can continue on. Okay, text section, pointers raw data, text section, header, virtual address. How do we deal with it here? We pass in the section header. Well, let's do it the same way. So this header, 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 and we have function encode. So now we're gonna pass result buffer. Okay, that looks good. And for this stuff, we can actually move the macro definition here and say get RVA. So that seems fine, except that this now goes into result. Result entry point RVA is get RVA. What are you unhappy with? Okay, we'll just deal with it one by one. Okay, it is unhappy with the macro. Yeah, because I did this to the buffer in the other code. Can do it here as well. That's not a problem. Okay, so we are out of issues in the code that actually does encoding, but we still have a few things to figure out. The first thing is this is not actually relevant anymore, but we need to do something about this code. So let's remove it from here. This virtual size we will now know correctly. So this is something that we need to patch in, and this is something that we need to patch in as well. Let's see what do we do about that. Yeah, I think it might make sense to get rid of this array, to be honest, because it's not really giving much to us. Let's see what that would look like. Well, it does accumulate the full size of image. Here's the conundrum. We need to know the virtual address of text when we are calling our encode text section function, right? Because we need to pass in here, and it needs to know both of these things. It needs to know where it starts, and it needs to know its virtual address. And we do know that because we know where our data section ends, but at the same time, right, size of raw data. Yeah, it doesn't know the size of raw data, but it does know pointer to raw data. But in order to know the next thing, we need to do that. Yeah. So we are going to disassemble this array, I guess, and change it into multiple loops. So we have S32 virtual size of image is 0. And we do this loop, right? We go through the sections, but then in this loop now we will only do try to figure out what is the virtual size of image. And for that, we will use the same code, I guess. How does it work? So we want to know the last non-virtual section alignment plus okay. So the way it's working right now is we just go through them and we record the next offset from the last item as a full size of the thing that we want to load. I guess that works, but won't be really what we want. So let's just say that we are gonna, what are we going to do? In here we write out those sections. So that's okay. And it's nice that it's a list. In here though, this doesn't even need to be a loop. What we want to say is text section header plus virtual address plus this stuff. So this is the So this is the size of virtual image because text section is the last section, and we are just aligning its size correctly, and we are getting the size of the image. Okay, that's good. What do we do next? Next, we have the size of headers, and we are using this for the virtual size of our data. And we also know we actually do know pointer to raw data as well, which was previously, I guess, yeah, which was previously updated over here, but now let's update it manually. So we say pointer to raw data is file size of headers. So this is our stuff for our data. Let's mark it up like this. Prepare our data section. Now we'll have the same one that says prepare text section. Okay, who was filling in the size of raw data? Was it done here? Yeah, okay, so mixed virtual size and size of raw data were filled in over here. I guess we can do the same thing here as well. It's not super elegant, but it will get the job done. Okay, obviously still have a bunch of errors, but that's fine. Okay, at least now we have code that should fill it in for right places. We can remove this stuff. And we can probably add an assert that will it be correct or not? No, this is not even longer correct. Like the number 10 that wasn't here, it wasn't true. And the code was still working, so I guess as long as the size of our data is correct, it's okay, but let's not rely on this. Let's fix it up. Okay. So this max code size, it actually has very little to do with the section itself, and is only necessary, I guess. Are we using it anywhere here? Like, is it even used? Doesn't look like it's used. So we don't actually need this. That's good to know. I guess where we want to put it is in here. Yeah, so in here we do want to check that buffer occupied actually fits into 32 bits, because Otherwise, these truncations are unsafe. But this is good. And now we just copy paste this text, fix a typo, and we say that text section header pointer to raw data is what? Well, it is this stuff, which is our data section header pointer to raw data plus our data section header size of raw data, and this is fine. And here it's basically the same, where we say that these two are we take the virtual address of our data section and we align the right thing here. So basically copy this stuff. So we take the size in the file and we increase the alignment to the alignment we will have in the memory. Okay, and this goes into here. So that's fine, except here it is going to be our data section header. Okay, I have encoded text section, encoded text section, that's fine. Did I name it? Yeah, I named it correctly, encode text section, so that's good. For the consistency, text section header. And now we can say that text section buffer is encoded text section buffer. Okay, that seems good to me. We can probably get rid of this stuff. It is not required. Say calculate total size of image in memory once loaded. So this is what the loader from Windows need to allocate for us to be able to start running. And this stuff, yeah, it is actually already going in here. We do need to fill in these two, size of initialized data and address of entry point. Size of initialized data is filled in over here. So this is like this, but actually we can make it better because we can take it out of our data section header, size of raw data. This is what it's supposed to be. And here we need to figure this out, and we will return it as entry point REA. So this is what we are going to put in here. We would say text or encoded text section entry point REA. Okay, this is not required. Let's see where we have issues. So the first thing is it's called text section buffer. That's good. Now we just have minor things with arrows versus not arrows. Just silly, but that's something we can easily fix. Encode text section, now that needs to return a value. That is very true. Let's return our result. And we are building. Well, let's see if I forgot something. It looks like I did. And this is going to be a bit of a nightmare to figure out. But let's start rolling on this. Dev what is it called? So let's open this stuff. and it is called mass solution. So def env mass solution. Okay. Let's first even see if this is at which point are we exploding, right? So it is not the tests themselves, right? Tests are passing fine. It is something in our executable that is not working like it should be working. So let's do a very quick review of what is happening. We call estimate max code size. We align it to file alignment. We like this buffer even doesn't need to be as big as this file alignment. That's fine, but it doesn't hurt us. Then we update these two things, which is file offset, which is header to, which is pointer to raw data. That's fine. And then we take the virtual address, which is what we need for our encoder to work correctly. Then we just go through all of the functions in the program and do this. Then we update the virtual size and we update size of raw data. So this seems fine-ish to me. Here we now just have a bunch of zeros, so this is also fine. File size of headers, this is okay. We can bring these two down like so. So this is more obvious what is happening. And let's see. So this stuff was working before, we didn't really change it. So the question is what happens here. Let's review. We have a text section located at the end of the our data section. So this seems fine to me. This is supposed to be aligned, but it should be. And here we are just taking the virtual address of our data and aligning this size to this. Okay, virtual size of image. That's also fine. This will now can also estimate, but let's not change more than we need to, especially because something is not working at the moment. And here we are. Let's review the fields that I changed. So this is our data section size of our data. That is probably fine. We can bring up the diff if we need to check what it actually is supposed to be, or it was before. And here we have entry point RVA. Base of code is virtual address. That's fine. This is alignment. Size of image, file size of headers. Well, all that seems pretty reasonable to me. Let's check what happens here. We create code memory. Yeah, all of this seems pretty reasonable to me, but it might not be. So what I will do first is I will just make a breakpoint here and start looking at some values if they actually make sense. Need to change my executable probably. Maybe not. So I guess I need to. Can I like make it here? This is very interesting. Why can't I have a breakpoint? Okay, apparently now I can. Fine. So let's just go through this. What do we have here? Size of headers, that actually looks like a reasonable number. I think that is what we expect it to be, if I remember correctly, and we didn't really change the logic here, so I don't expect it to have a problem. We align it to file and we end up with 200. So looking at stuff over here, like this seems pretty reasonable. Then we have virtual size of headers. So that's gonna be 1,000, and that looks also quite okay. We update our data section. So this is gonna be at the offset 200 in the file, and the virtual address of it is 1,000. So that's also what we expect to happen. Okay, what's next? I will not go into encoded stuff because we didn't really change it, so I don't expect it to break, but maybe it will. And we have the buffer. Okay, what happens to text section? This is stuff that is more interesting. So first of all, pointer to raw data. It is at offset 400, which is exactly what we wanted it to be. So it's right after the RData section. And as far as the virtual address, it is 2000. So that's also correct. Okay, let's jump into encoding thing. We have max code size, which is 200. So that's fine. Yeah, it does fit into 200 bytes. And then we make the buffer. We continue here. And we can look at program codebase file offset is 400. That is very true. I guess, yeah, it is correct. And RVA is 2000. So that's all of that seems pretty fine to me. Let's go through this. So the first function that we encode is not the entry point. The second function should be, so result entry point RVA is 2022. So that seems fine. I'm not sure what is going on. Okay, we assert that we fit, we update virtual size. Virtual size is 30 bytes. I can believe it that it's 30 bytes. And we do what? We check here. So that all seems very fine to me. However, I'm now wondering that our encoding actually might be screwed up because of the way it is calculated. So let's take a quick look over here. And I want to look at our import code. What does it do? So next instruction RVA is this stuff. Yeah, is now incorrect. So the first thing is we don't need this anymore because we are encoding into a separate buffer. And so here it will be actually program code base RVA plus buffer occupied. So we don't need that base file offset. So let's get rid of it. Oops. Base file offset. Okay, we don't need that anymore. So once we remove it, we'll know where we are using it, so we can get rid of it. Yeah, it happens here. So no minus here. So it is now just buffer occupied plus size of 32. So this is way more reasonable. And interestingly enough, it is also exactly the same thing as here. So I guess we should be able to merge this code together back. Okay. Maybe this one deals with library names. I don't know. We'll see how it goes. For now, though, what is going to happen? Yeah, that's fine. And in here, we also don't need to assign it anymore because it's not even used. Okay. So that builds. And let's see if this is any better. And look at that. We have our 42, which is great. Let's add this to the index. So we have a nice chunk of work done. And looking at this code now, it's not the prettiest code in the world. That is very, very true. And we also need to free the text section buffer now. So let's check that. Yeah, still fine. Again, not the prettiest stuff. Again, definitely a lot to be done. Some of it might not be very pretty in C if we want to do it. But let's try to get rid of these last remaining hard-coded things, right? So this one I will not touch. We will stay with the console UI for a very long time because the whole UI programming on Windows is really terrible and I don't want to get into it anytime soon, if ever, on this series. But this is something to do if we were doing a real language. But this sizing is something that is gonna bite us in the ass at some point, so let's deal with it. And now we can actually know what is the right size, because we can say that U64 MXXE buffer is gonna be what? Well, it is gonna be our data section buffer occupied, or rather, no, we shouldn't look at buffers, we should look at size of raw data. So what we need to do is file size of headers, right? It's definitely will have all the headers, plus it will have our data section header size of raw data, and plus the same thing for the text section. Okay, and we can do it here. Let's see if we can still output stuff that we need to do. Great. And just to verify what happens is, let's just say -100, just to see if this will explode in any way. I guess it doesn't, because, yeah, because we are overestimating everywhere, but that's fine. Okay, so that's the maximum size for the executable, and we can add that to the index. And the last one we have is here. Now, I guess let's just make it happen. So the way that would work is we would say U64 max encoded size is 0, and then we'll take one of these loops, but instead of actually doing stuff, we will go through the stuff that we will need to have to output it to executable. So we'll just start filtering code, right? We don't need these, but we are appending S16, so we say max encoded size plus equals size of S16, and we can even keep the nodes so we know what we are reserving for. Now we have this name size and line name size. Unfortunately, we have to keep this logic, but we say that max encoded size plus equals and this stuff. So this is what was it? Was this? I guess it's import address. Yeah. Okay, that's one block of stuff that we need to do. And let's look at other blocks. So here we are appending U64, and it's also 0 terminated. So max size is plus U64. And we also want 0 termination, right? This is this stuff. And so this is, I guess, IAT. So import address table. Okay. You can put comment here as well. Now, in an ideal world, we would be able to express this encoded stuff as some kind of data structure. It will just say that put this field over here, put this field over here. But it is very awkward to do that in C. I guess we could try to, but I'm not sure it will be worth the effort for this kind of stuff. Although it might be a fun video to try to do. Let's see how that goes. I think this is unnecessary. Let's try to remove this, because I think it's the same as this stuff. Yeah, that looks to be just not required. Okay. What happens here? This is where we write out library names. This is the same thing. So I guess I can do this. Name size. Oops, that was the wrong place to do it. This over here. And we need to do this. Okay, and here we will call this, actually we will just do it like this with a comment. Align string, or maybe we put comments on top. Align string line to 2 bytes C string of symbol name. Okay. I think this is a placeholder for function pointer or symbol pointer. Yeah. And now we can do the same thing here for the library name. Align the sim of library name. Okay. So that's better. Sterling, yeah, this needs to be lib. What is it called? Lib. It's dll.namer. Okay. dll.name. Okay. That looks good to me. And what else do we have? Well, we have this image directory where we do a bunch of descriptors, and then we output this direct one. Okay. So that means that we need to take the size of this thing and say, and add it on every iteration, and also 0 terminated. So this is image thunk, and we say max encoded size plus equals size of this, and we can add one here as well. Okay, this is also zero termination. For consistency, let's move it here, and we have probably the right answer. We can even change the name max encoded size to encoded size or expected encoded size. And now we have our expectation, we have our reality, and we can verify that those two match. So let's do that and see if we have missed anything. Buffer occupied is expected encoded size. Let's run the test. And it isn't. So let's see what is happening there. We can set a breakpoint over here, launch it up, continue to the right place, and there is a difference of 16 bytes that is happening somewhere. Okay, let's review what we have. And I can actually use this editor here for having two parts. Okay, so this is the first loop. In the first loop, we do buffer append S16, so this stuff. And we also have a line string. So that's taken care of. That seems fine. Then we have a second loop. And in that loop, we are just doing buffer append U64 and one at the end. So this is this stuff, right? Okay. What is happening in this loop? Oh, we have basically, we have two loops that are doing this 64-bit stuff. So this is where the problem is. And actually it is a separate thing here that is image thunks. And this is import directory. Okay, let's try that again. Still not happy because it's supposed to be like this as well. For directory, zero termination. Okay, let's try now. And we are good to go. Okay, that means we now can replace this hard-coded buffer with the real number, and we can replace this stuff. Actually, this is a good assertion to have. It's still going to be true. So let's try that. Okay, so now we have basically zero hard-coded things in here because this number doesn't matter. These numbers are all very standard. They are expected to be that way. Obviously, in a compiler, you would like provide command line options or some other way to configure this stuff, like how big is your stack, what subsystem you want on Windows, and things like this. But in general, it is not a problem of calculation. And we also actually don't need this stuff. So yeah, I really like how our PE32 executable writing out code is looking like right now. Again, it would be very nice if we had more expressive language to deal with to not repeat this logic, but it is okay for now. With that, I thank you very much for watching. This brings to an end this three-part stuff on cleaning up PE32 executable writing, and next time we will do something a bit more exciting. For now, thank you very much for watching, and see you then.